We're going to do a mini neutrino fest in the next hour. And you already heard some neutrino talks yesterday from Pedro and from Michael. So we've coordinated these talks in such a way that we are trying to avoid overlaps. So if you see certain things which are not covered in my talk, it's because other people will touch on them. So the assignment here is to talk about a few, let's say, problems in neutrino physics or urgent issues. And I want to make a couple of basic comments about the status of the field. So first of all, neutrino physics, since about the turn of the millennium, has seen an amazing pace of experimental developments. And this is still true to this day. So we are living in an environment which is flooded by data. And this data leads us in areas that we sometimes could not have foreseen 15 or 20 years ago. But such is the life being driven by data. And then modern neutrino physics is a very rich and multidisciplinary subject. And a curious consequence of that is that there are certain logistical issues. So, for example, the neutrino mass matrix, 3x3 matrix, has been split between offices of DUE. So, you know what I'm talking about. The solar angle is firmly in the nuclear side. And then theta 1,3 is funded by both. So I'm going to talk about some recent developments. I just did a sampler just to give you a taste for what's happening on the experimental side, so you don't think I'm making it up. So I'm just looking at one journal, Nature. So here is an article from April of 2020, where the G2K experiment in Japan claims first signs of CP violation, which, you know, would be a fundamental discovery in basic physics. I will return to this question a bit later, but obviously this has been a very high visibility result. And then a few months later, the Borexino experiment reports observation of what's called the CNO neutrinos, which is another way of fusing hydrogen into helium in stars compared to the PP chain, which dominates the sun. But this process dominates the energy generation of massive stars. And so this work provides experimental evidence for the primary mechanism of stellar conversion of hydrogen into helium. And there are many detailed implications for the physics of the sun. For example, the solar metallicity. IceCUBE reported last year an observation of the Glashow resonance. So this is where a PeV neutrino, well, more precisely a 6.3 PeV neutrino, comes and strikes an electron and makes a W, which then creates a shower. And so as such, they can now see that there is an anti-neutrino component. And so in addition to information on neutrino flavor, they now have some information on neutrino and anti-neutrino composition. And that should facilitate the advancement of neutrino astronomy, the understanding of the sources and the production mechanisms. Okay, and just this week, there is an article from the KATRIN collaboration on their direct bounds for the neutrino mass measurements. And you can see as of now, it's about less than 0.8 eV. So that's just a broad spectrum. I didn't mention many things. Now you'll be right to be upset that, for example, what about microboon? Well, that's obviously a big development of a few months ago, and there are many other experiments. So this is not complete, just a sampler. So one thing that we as a field have come to recognize is getting to be pretty important and pretty urgent is the physics of neutrino-nucleus interactions. And so I'm going to spend a bit of time on this in a bottom-up approach, so in a pedestrian way to explain why we care and why we didn't have to care up to now. So now our field went from this is an actual snapshot of the 1996 PDG, where it says no direct uncontested evidence for massive neutrinos or lepton mixing has been obtained, to this, where we have Nobel Prizes and fundamental physics breakthrough prizes, and there's now a set of very well measured oscillation parameters in the 3 neutrino framework. And so we went from there to there, and so far, you know, we did have to worry about neutrino interaction physics, but not as much. So what changes now? So what changes is that the usual thing when you go from the discovery era to the precision era, things that you could not worry, finally you have to worry about it. So in these early experiments, we were talking about very large effects. So the atmospheric neutrino depletion is about a factor of 2. And in the case of solar neutrinos, the famous Homestake experiment was seeing about 1/3 of the predicted flux, and the Snow experiment conclusively showed that the neutral current rate is 3 times higher than the charge current rate. So these are large observables and they are robust. And now in modern studies, when we talk about subtle effects like CP violation, mass hierarchy, and new physics, we're talking about 5–10% effects. And so then we have to, there is a, just like in the LHC, when precision is pushed and folks have to compute entry-low corrections, then so is it's true for neutrinos. Now the goal here is precision studies of neutrino oscillations as a function of energy. So there is a survival probability. This is the survival probability for DUNE for 3 choices of the delta phase. You can see that they differ a little bit, and this is the spectrum. And so since we are trying to determine survival probability as a function of energy, reconstruction of energy is key. Okay, now here is what an event at DUNE looks like. This is not an actual event, and this is a simulation. But you can see that since we are shooting neutrinos of several GeV, the final states are complex. So there is a muon in the final state. This was a muon neutrino, and this guy is easy. But then there is also a proton, and this proton goes some distance, and there goes a secondary interaction, and then there is a pion, and it undergoes secondary and tertiary interactions. So the topology of these events is complex. Now, this halo is not a bug. There is a halo of small charge deposits that's mostly due to neutrons, but also due to Compton scattered electrons from gamma rays that are created at various stages of this event. So the events are messy. And we cannot, because we do not know the final state mass of the hadronic system, it varies, then we cannot figure out the energy of the neutrino from the muon alone. And we have to use calorimetry, which is okay. I mean, that's not a bad idea by itself, but then the calorimetry is not complete. There are known missing energy channels, and we have to fill them with generators. So, for example, there are neutrons which are created in these events that, most of that energy is just genuinely lost. And the little bit that is not lost needs to be associated with the event very carefully. So generators have a very important job for this measurement. And you can say, well, okay, does that really matter? So here's an example of something which has already been happening. So if you look at this plot of global fits and measured angles, let's specialize to this guy. So this is the 2-3 parameter space. And you can see there is a region measured here. You can unpack it, ask where does it come from. It comes from several experiments, but the main one is NOVA here. This is the experiment where neutrinos are shot from South Dakota to, from Fermilab to northern Minnesota. And you can see there is a region where the maximal mixing area is included. How does that work? Well, there is a set of events as a function of energy. Unoscillated, you would have a huge peak here. These events are depleted by the oscillation. And so because of this, the depth of this suppression tells you the amount of the amount of mixing you have. 45 degrees means maximal suppression. And then if you go back and you look at the NOVA results 2 years or 3 years before, they were finding what looked like non-maximal mixing. And the only thing that changed in that case is that they had a few events here. And so they thought they discovered non-maximal mixing in the theta 2-3 channel, but it turned out that these events just did not have their energies accurately measured. So once they improved their measurements, these things migrated out and maximal mixing is back in place. So it's important to measure energy, and cross sections are important in this process. Now, what do we know about the status of the generator codes? Well, we have to test them, and one way to test them is to flip the switch to electron scattering, where you have precise kinematic control. And so you can separate different processes, elastic and inelastic. And here's a data set collected recently, a few years back, at JLab in a 2.2 GeV electron beam. And here is the Gini generator compared to that. And you can see this peak, which is the quasi-elastic peak. The width has to do with Fermi motion of nucleons inside. This peak is actually pretty well reproduced. And then the moment you go into the inelastic regime where you're making pions, then the technical description here is terrible. So you can see that we have some quantifiable ways of showing these discrepancies. And this is the regime where DUNE and NOVA operate, especially DUNE, since most of the events are inelastic. Now, you can simplify things by looking at the simpler targets like deuterium and hydrogen. And there is a pattern in this inelastic regime of discrepancies, which is very large. And if you think that I'm picking on this specific generator, it's actually not true. I mean, there is a comparison across different generators and different versions of the generators that was presented by Arthur and Csaki in our neutrino program earlier this week. And different generators struggle in different ways. Some overshoot, some undershoot. But in general, this problem is not solved well right now. Now, we also had a talk by Daniel Boris, also earlier this week, where they look at this problem from the neutrino experimental side. So he is on the Minerva experiment, which has a job of measuring neutrino nucleus interactions at Fermilab. And so this is what they find. They try to fit their pion, their inclusive pion production data. And they find that a bunch of generators with different settings all give you terrible fits. So they have 205 degrees of freedom, and chi-squared values are 5,000, 7,000, up to 12,000. So yes, that's the status. Now, this is a very lowbrow introduction, but what's actually going on? So what's going on is that we have a problem where, well, we decided to live between perturbative QCD and nuclear physics, where we need to design a theoretical framework that's more robust. So, for example, it has to respect the quark-hadron duality and not double count resonances and DIS contributions. And this is, here we heard several times that in theory, we are interested in the description of field theories in transition from weak coupling to strong coupling. Well, this is such a theory, and this is such a problem, and it's not easy. But we know that like quark-hadron duality works extremely well at JLab. I mean, this is old SLAC data, but it works very well, and then we have to respect that when we're building this. Well, you can say, well, why did we choose such a terrible energy range to carry out our experiments? And that's driven by oscillation physics. And I can answer that if there are any questions. So it's actually the parameters of the oscillation world that drive you there. Okay, now, another new branch of neutrino physics is lattice QCD. And that it comes about because we also need accurate determination of axial form factors. Lattice has made tremendous progress in this problem. You heard that from Michael yesterday. Plus, next week in our neutrino program, we have the entire lattice test by different groups. The story here is that understanding form factors of nucleons is much harder than the corresponding mesons because of noise and excited state contamination problems. And they have recently figured out how to identify and subtract these. And so several groups here are showing this is their results before the excited state subtraction, and this is their results with the excited state subtraction. And noticeably, they all agree. They all conserve PCAC now, but they disagree with the old dipole parameterization that has been fed into our neutrino generators. So there is an implication of what we have in our modeling from lattice QCD now. Now, okay, now what about putting experiments together? So I mentioned the T2K claim that they see a CP violation. Basically, the way it works is they see a lot of appearance from muon to electron neutrinos and relatively few disappearance. And if you make this by probability plot, this pushes them towards one corner where CP is maximally violated. And then if you look at Nova, Nova actually is here. So if you think that you are in the same normal hierarchy, so these are for normal hierarchy, as you vary the phase, then these two are in tension. They prefer opposite phases. So this nice paper by Kelly, Pedro, and a bunch of Fermilab folks, they have observed that if you put them together, the tension actually pushes you to inverted mass hierarchy. And so combining experiments can be very important at this point. And of course, you know, if you add a little bit of new physics, maybe this discrepancy as you sharpen it is a sign of new physics. For that, we need better measurements. So DUNE and Hyperk are going to be crucial to resolve this story, whether there's actually a tension, a statistical fluctuation, some unaccounted systematic effects, or new physical effects beyond the standard model. So I'm going to say very little about this exciting topic, mainly because I have an excellent talk. We have an excellent talk by Zara that will follow this. So neutrinos present an excellent opportunity to search for new physics effects, both with light mediators and in frameworks of EFTs. So she will highlight this. You know, neutrino near detectors are spectacular. They're well instrumented. We have huge event rates. On the other hand, accurate measurements of oscillation parameters provide essential inputs for models of flavor. And Michun will also talk about that, and we'll talk about that. And then Pedro talked about the short baseline situation, which is very important for us. We have to get understanding for what it is that mini-boon has seen. They claim together mini-boon SMD up to 6 sigma significance. Microboon has not been able to identify what it is that they see, but we have to understand it. If we are to do precision experiments in the future, and even if there is some hadronic effects that has not been accounted for, we have to be able to identify this. So this is the job for the short baseline program. Oh, 3 minutes. Wow, much better than I thought. So now I'm going to do a lightning review of the other branches of neutrino physics. Cosmology is one of them. So if there is a sterile neutrino or some light fermion, in addition to the 3 active neutrinos, cosmology becomes very, very interesting. The maximally minimal scenario, where we have a sterile neutrino with such a large mixing angle from the cosmological point of view, is immediately in tension with BBM and CMB. From Planck, we know that neutrinos in the early universe contribute to the evolution of density perturbations. Namely, when they first enter the horizon, they are part of the gravitational budget, and when they stream out, the phase and the amplitude of the oscillator changes a little bit in a predictable way. So we know that the number of effective degrees of relativistic effective degrees of freedom is close to 3. Most of them free stream, but there is room to have fractional and effective. And this drives a lot of scenarios with hidden neutrino interactions, so-called neutrino portals, where this recoupling can be suppressed, but not completely. And so right now we have bounds from Planck, but the Simons Observatory is planning to push this error bar down to 0.05 species. And so if there is something in the short baseline, maybe there is some corresponding signature of that in cosmology. For supernova neutrinos, I want to just say something very, very briefly, because this is such a beautiful problem, such a fundamental ingredient of our universe, and it's very rich. So you can, in 2 words, you can say there is a core of a massive star that reaches a certain magical mass called the Chandrasekhar mass, which is m Planck cubed over m nucleon squared. It's made of the fundamental quantities, constants in nature. Somehow this is of order solar mass, more precisely 1.4 solar mass. It becomes unstable, it collapses, and the gravitational binding energy of this object is about 10% of its rest mass, and it comes out in a huge burst of 10 to the 58 neutrinos. The time scale is set by weak diffusion time scale, so it seems to be consistent with that picture. And less than 1% is diverted to the visible explosion and becomes an obvious, a spectacular event that is bright as the rest of the galaxy. So people are trying to understand how that works. There are also neutrinos to be observed from such events. We've seen one 35 years ago. So this week earlier, we had the 35th anniversary of the 1987A event. And when the next one happens in our galaxy, we're going to have thousands, perhaps tens of thousands of events. And so we can ask much more detailed questions. And so that's what drives one part of DUNE, for example, and Hyperk. Now, the physics of oscillations here is much, much richer than in the sun or in the lab. There are several MSW resonances. There are density discontinuities that have to do with the shock. There is a stochastic profile here, which is turbulent, where you have special treatment for the flavor transformation mechanism. And then here, there is an amazing region where neutrinos oscillate collectively. And that's basically all I want to say here. There is a region where the streaming neutrinos have such high densities that their flavor evolutions become coupled. So you can think about 10 to the 8 moles of neutrinos per cubic centimeter. This can never be reproduced in the lab, but the supernova does this for us. And then one has to evolve this ensemble of neutrinos as it flows out and expands. This is a rich many-body quantum system. We saw many spectacular and weird things about this system over the last 15 years. And we're certainly not done. We still don't understand it fully. But what we know is that it impacts what we will see on Earth, and it impacts nucleosynthesis that happens in this star. So if the next time we see a supernova, if we know how to read it, we can learn about the mechanism of the explosion. We can check whether the physical conditions were right for certain types of nucleosynthesis. Can explore quantum dynamics and dense neutrino gases. Can say something about the compactness of the central objects, so the equation of state of nuclear matter. And many probes of new particle physics, which, as you know, already exist based on 24 events from 1987. It will be much more powerful once you have the thousands of events. Other neutrino topics are not mentioned in my talk. Well, the ones that will be mentioned here are coming right after me, but there is an incomplete list of things like neutrino dark matter interactions and the LHC and things like double beta decay, the origin of the neutrino masses. If any of this sounds interesting to any of you, we are running a program right now. It is running in person at KITP, and next week, as I said, we're doing live STCD fest. But you can connect on Zoom, and please ask us for the link, and you will connect on Zoom. So you can see the richness of the topics here. This kind of reflects where the neutrino field is now. So thanks.
Questions?
Questions, complaints?
Alex, Jesse Thaler. On the generator side, there's kind of two things that you might think would be uncertain. One would be, the like Genie style things, the generator process, the kind of truth level, and then one might be understanding the detector response. Right, I think you talked about the first one, which is of course more of the theoretical side. On the detector response side, how well is that understood?
So the thing that I showed you at first was the detector response part. Now the interesting thing is this was simulated by theorists at SLAC, a brilliant postdoc who is now went to Fermilab, and her collaborator, who is standing here. So